All right, so welcome to our second session on Arduino. So this session is about motors, so kind of outputs from your Arduino so we can control things. And today we have a new presenter. So you've seen Michael for the past 4 programming side sessions. And today we have Lila, who's a grade 11 student at Blue Vale and is on team 2702. I think everybody's already renamed themselves, so we're good there. If you have any questions, feel free to raise your hand, type them into the chat, or you can also unmute yourself. And yeah, I'll just hand it over to Lila. Thank you.
All right. Hello, and welcome to this workshop on motors and how to control them with an Arduino. So before we get started, as Eric said, but you already did that. I suggest though going into Tinkercad circuits if you haven't already and start a new project so that when we actually get into the wiring and the code, you're ready to go. All right then. So what kinds of motors are out there? There are different kinds, and the more common ones used in robotics are DC motors. There are brushed and brushless motors, and there are advantages and disadvantages to both. Brushed motors tend to be easier to control and cheaper, but brushless motors, although harder to control, are generally faster and quieter. And you usually use these kinds of motors for if you have a high load or if you just want to turn quickly, like for drones or for cars. Then there are servo motors, which are used for precise movements with high torque. And there are positional motors that you can set to specific angles, and then continuous servos where you set their speed and direction. And then there are stepper motors, which can be used to also set precise positions or steps. But they are also a little harder to control than other kinds of motors. For the challenge, you'll have brushed DC motors and servo motors, both positional and continuous. So that's what I'll cover today. So the way you control motors is using something called PWM. Now you probably know that if you stick a motor to a battery, it'll turn, but that's not very exciting because it'll just turn in one direction and at one speed. But using pulse width modulation, you can actually control the speed of a motor. And the way this basically works is that you switch the power to the motor on and off very quickly. And it's actually in the microsecond range, which is a millionth of a second. So for motors, a pulse width is generally like 2000 microseconds. So you don't feel this switching because the inertia of the motor and because these time intervals are very short. The duty cycle is the amount of time the power is turned on within a pulse. So basically, depending on how big the duty cycle is, the faster the motor will be if it's a DC motor. For servos, it's a little different. And so this gives you control of the motor because what you effectively do is you can control the average amount of current that's supplied to the motor. And if there's less power going to the motor, it'll turn slower. If there's more current, then it'll turn faster. And these graphs kind of show this idea. The pulse is given continuously to the motor, and you have an off period and an on period and an off period. And so the duty cycle is the ratio of the on period, the peak relative to the whole pulse width. And the off period is the trough of this graph. So the lower the duty cycle, the slower the motor will be, and vice versa. All right, then, let's go into Tinkercad circuits, and let's wire up a DC motor. So what you'll need is an Arduino, a DC motor, and a breadboard. So take a second to put these on your project, and I'll actually switch to Tinkercad. So if you go on to the bar on the right, if you haven't done this before, you select an Arduino, a motor, and then you can also just search a breadboard, and it'll come up. And you want to have a signal, a wire coming from one of the PWM pins to a resistor down here, and a wire coming from ground to the uh, to the negative sort of line on the breadboard, and the 5-volt coming to the positive side. And so Michael touched on this last time. On the breadboard, the negative, this whole horizontal line is connected to each other, so anything you connect to it is connected. And same thing for the positive line, and all the vertical lines are connected, each of these 5 pins. So if you have, well, let's take a closer look at this circuit down here. Now I know it looks a little complicated, but I'll go through it. So you have the signal coming from the Arduino, and it goes to this resistor, which is connected to a transistor. And if you don't know already, a transistor is kind of a digital switch. If there's a signal supplied to the transistor, it'll turn on this circuit, which powers the motor. If there's no signal, then the motor will be switched off. And so the signal has to go to the middle pin, and you can set the resistor to the default 1 kilo ohm. Then on the left side of the transistor, you have a wire going to ground. And remember, all the pins on one vertical line are connected to each other. And on the right, you have a diode connected to the transistor and the ground of the motor. And so a diode only allows the current to flow in one direction, which is why it's important to have this white line facing away from the transistor. And then on the other end of the diode, you connect the motor to the positive side, and you connect to the 5V of the Arduino. So take a moment to wire this up, and if you have any questions, drop them in the chat. I'll zoom in here. Nope. And so this circuit has several advantages. For one, you can give a PWM signal to the motor, and it also protects your Arduino because it isolates the motor from the board. And the reason why I want to do that is because DC motors could at times draw up too much current than what the Arduino can supply. And if that happens, you can fry some of the inner electronics. And I think Michael and Eric touched on that last time. And so you want to isolate the motor, and this circuit does that. Yeah. Any questions? Also, if you're done or you want to move on, there are these icons in the participants tab that you can press to let me know. And if you want to turn any of these components, you can press this icon here. All right, then I'll take the silence as people being ready. So yeah, you never want to directly connect a DC motor to an Arduino because it could damage the Arduino, and also if connected directly, how are you going to supply the PWM signal? And so it's circuit is important. And one thing I'd like to say for the Illigo challenge, when you get the kit, you won't have to worry about making the circuit or making it correctly, because you'll be supplied with something called an H-bridge, which allows you to connect the motor to the Arduino, and it has similar circuits inside that allow you to control the motor. But it's good to know about this stuff so you know if something goes wrong, where it might have gone wrong. All right, then, let's get into the code. And so last time Michael showed you how to wire an LED and how to program it. And so it's the same thing for setting a pin for the motor. And so you say pin mode. First parameter is the pin of wherever you connected the motor to, and you set it to output. But in the loop function, what's different is that instead of digital write, which is what you used for the LED, you'll use analog write, which sets a PWM signal to the pin. The first parameter is the same as the pin that you've connected to, and the second parameter is the PWM signal, and that can range from which stops the motor to 255, which is the maximum. And so you have overall 256 different levels. So back the code here. If you zoom out, sorry. If you run it, if everything went correctly, you'll see the RPM increasing. So this program only allows motor to run at one speed. So to spice things up a little, I'll show you something that you can do with the serial terminal. And so last time Michael showed you how to write to the serial window. This time I'll show you how to read from the serial terminal. And so what you do, just like last time.
And we have a question maybe just before we get to that.
Okay.
So just a question on that, on the hardware. So Connor's asking, do we need to choose a pin on the Arduino that's got the little tilde symbol next to it to use this motor?
Yes, it has to be a PWM.
Thank you. And just a comment from Jeff. He was saying that he used pin 2 and it worked. I wonder, what was your RPM, Jeff? Was it well over 2,000? Because what you might be getting in that case is yeah. So you're essentially getting a full on. So you're getting full power. It's just like connecting directly to the battery. If you use PWM, you should have gotten in the 2,300, 2,500 range.
Yeah, what I found is if you actually try to run this code on one of the non-PWM pin, then half of the values, the upper half will be as if you supplied high, and the lower half will be 0 or low. So you won't have that range. It'll work, but not the way you want it to.
Makes sense.
Yeah. Yeah, and you can try changing around this number and running it and see how it changes. So now the RPM is in the 200 range instead of over 2,000. Right. And any other questions? All right then. So for serial input, what you do is, again, you'll write serial.begin and set it to 9,600. So it's the same setup, but now in the loop, what you do is you'll make something called an array. I don't think we've talked about this before, but an array is basically a list of something. In this case, it's char, which stands for character. And make this input, and we'll maybe make 5 characters. So this will be a list of 5 characters. So what we'll do with this is we'll check if serial.available. So what this does is we check if there's anything written in the serial window. And if there is, what we'll do is serial.read bytes. And what this does, it reads whatever it is that you wrote. And it reads 1 byte. Well, okay, not 1 byte, but it reads whatever bytes you give to it. And so in the first parameter, you write the array or whatever container it is that you want to store the input in. And the second parameter is the number of bytes or characters that you want to store in that array. And so in this case, I wrote 3 because you'll never have more than 3 digits in the PWM signal. And so you might be wondering why I used 5 up here. It's just a failsafe in case anything goes wrong. If there are somehow more bytes than what I expected, that the program will immediately crash. So what you'll do next is actually let's declare a global variable. Let's call it int speed. So what we'll do, and let's initialize it. What was that? Anyway, we'll set speed. So now what we stored the input into an array, but we can't really use that. We can't give it to the analog write function here. So what we do is we take speed and store whatever it is that we had in the array and convert it to an integer. So this is what A to I does. It converts an array to an integer. And what we put in here is input, because that's the array that we want to convert. And so now we have an integer stored in speed. And that's it. Now all you have to do is write speed in here. And whatever you write in the terminal, that's what's going to be given to the motor. So if you run that and open the serial monitor, so now it's at 0 RPM, set speed 2. If we write 100, the speed will increase. If we bring it back down to 20, the speed should decrease. But it's not decreasing. Oh, it decreased. Never mind. So now it's back down to 200, which we had previously. So any questions about that? Sorry. So everybody got that? All right then. If there are no questions, I will move on. Right then, let's look at servos. As I said before, servo motors are used for precise movements that require high torque, and one application for that would be turning the Elegoo car. For positional servos, the PWM signal, unlike with DC motors, actually controls the angle, so it'll set the shaft to a specific position. And for positional servos, you usually have a range between 0 degrees and 180 degrees. Some servos might go up to 270, but the ones that you'll be using only go up to 180. For continuous servos, the PWM signal controls the speed, and you can set the speed in either direction. And continuous servos can rotate continuously, just like a DC motor can, but you can control the speed a little more. Like they tend to be slower and give off a high torque. And so if you think in terms of degrees, with the maximum being 180, if you want to control a continuous servo, half of the values would correspond to the speed in one direction. So the wiring of a servo is simple. It's a lot simpler than a DC motor. You can connect it directly because servos don't use as much current as DC motors do, and they also have an internal board that also isolates the servo a little. And so you have one wire going to signal, the red wire going to 5V, and the ground going to ground. If you want, you can start a new project. You could also just build on the one that you started now. But I recommend starting a new one so you can also retain the code. And let's say you want to connect the servo to an external power source. What you do is you'd connect the positive to the positive side of the battery. You'd have a ground going to the Arduino and ground going to the ground of the battery. So you have two wires coming from the ground pin of the servo. So you can complete the circuit on the Arduino, and you can complete the circuit on with the power source. And by the way, if you wanted to do this with the DC motor, you do the same thing. We'd have, instead of the positive going to the Arduino, you'd go connect to the motor, to the battery, and then have two ground. Questions on that?
Maybe it's worth saying, if you want to create a new one and you haven't figured out how to do that, click the Tinkercad icon in the top left, and then you can create a new design.
Yeah, I know. I just used the battery as a demo, but you want a 5-volt power source for the servo. Yeah, don't use a 9-volt. That'll destroy your servo. Thanks for putting that up. Yeah, if you actually try to connect the servo to a 9-volt battery, it'll show an explosion in the simulator. Okay. Now let's go to the code. So we'll include the Servo.h class, make a servo object, and in setup, instead of using the pin mode function, you'd use the object to call the attach function, and as a parameter, you'd write the pin that you connected the servo to, and once again, you have to connect the servo to a PWM pin. And then in the loop function, what you do is also use the servo object and call the write function, and in the parameter, as an argument, you'd write the position that you want to set to, and so 0 would correspond to 0 degrees, which is the minimum value, and 180 would correspond to 180 degrees, which is the maximum. And you can write whatever value you want in there. And between each command, we'll delay for 1.5 seconds to give the servo time to get to that position. And that's important because you don't want to overwhelm your motors. So I'll go back here. Are there any questions on that? So if you run this code, the servo will keep switching its position. So 90, 180, and then back 0, and so on.
Could you put the code back up there? It was a lot to look at.
All right. I'll just any questions? Okay, then. If you're ready to move on, let's try something a little more complex for the servo. So you cannot directly control the speed of a positional servo. However, you can do it indirectly using the delay function. And I'll demonstrate this through this sweeping motion program. So what this will do is it'll sweep the servo back and forth, and you can control the speed of that sweep. And so we'll have 2 for loops, one to sweep it in one direction and the other loop to sweep it in the other direction. So in the statement, we'll set the angle to 0 and have it go up until 180 degrees or 100, yeah. And then write the angle to the servo and delay for 15 milliseconds. So naturally, the bigger the delay, the slower the motion will be, and vice versa. For the second for loop, we'll do the same thing, but in reverse. We'll start at 180 and go down to 0. And that will sweep in the other direction. So you can comment out the previous code and write this. So I'll go back here. Comment this. And if you ran this, I'll actually move the servo here. and start the simulation. Now you'll see it'll move back and forth. Are there any questions on that? So from here, what you do is, oh, yep. Orange highlighted code. So what does there say? Oops. Oh, you mean?
I'm actually wondering if it's an error in the code somewhere or a warning or something of that sort.
Might be, but usually when the code didn't work, it highlighted it red for me, but orange might be a warning. Does the code still run?
It had happened on the previous one. I had an error. I repaired the error in the code, and it retained some orange, maybe red in your case.
Oh.
I wasn't sure if it's continued errors or a suggestion or what.
I had the same thing. I think it's a bug because the lines that were highlighted, I hadn't included Servo.h, and it gave me 3 errors, and now those lines are still there, even though they're not the right lines anymore, and one of which is a blank line between functions.
I have the same thing, a blank line.
Yeah, it's probably a bug, yeah. Yeah, I think this simulator is fairly new, so I'm not surprised. So from here, you could actually just change the angle, for example, narrow the range that it can turn to. And what that'll do, it'll just sweep back and forth on a smaller range. Then, are there any questions on this? Okay, now we still haven't looked at continuous servos yet, and what you can do is you can click on the servo and change its type to continuous, and that'll put this wheel on there, and you could run this code and it'll work. The output will be different though, as you can see. So what's happening here is it's speeding up in one direction, reaching the maximum speed, in this case 120 per 70, and then it slows back down to the range around 90. It stops momentarily until it speeds back up in the other direction, and it keeps doing that.
You're breaking up for me, Layla. I don't know if anybody else is. I think maybe that simulator's hurting your computer a little bit.
It's happening for me as well. I was assuming my local 2 other streaming people were causing the issue.
So maybe just hit stop on the simulator while you talk.
Okay. Is this better?
Yes.
All right. So to reiterate, what this does is it speeds up until it reaches the maximum angle you set here, or speed in this case. And then as the loop progresses, it slows back down until it reaches the middle range at 90. And it stops momentarily, and then it speeds back up in the opposite direction. And if you want to see this better, you can maybe make the range even narrower, which would actually, let's set this to 80, and then you can maybe better see that it's actually switching directions. can make the delay bigger. So if you run that, you can see that it switches directions. So any questions on that?
Yeah, I think the key takeaway for positional servos versus continuous servos is just that one of them can be used as a wheel and the other one can be used to move something like an arm or a device that just doesn't have full range of motion. And a continuous servo is really just like a easier way to implement a DC servo because the controls may be a little simpler. You don't need that external hardware to drive it. So
yeah. And especially if speed isn't really much of an issue.
Quick question.
Yeah.
A servo is relatively low torque. Agreed?
These ones, yeah, but there are some servos that go up to like 20 or 30 kilograms per centimeter, which is
a lot.
Yeah.
I'm thinking the hobby type ones. More for control surfaces like in airplanes or steering in a car.
Yeah. For like more heavy duty applications, then yeah, they'd have a lot more torque. But these ones, they're not that strong. I think it's at 2 kilograms per centimeter. But for our purposes, it'll be fine.
And I think they're way more than a DC motor. If you grab the wheel on a DC motor, it'll stop way more easily than you do on a servo typically.
Yes, if they're similar size. Yeah.
Exactly. Yeah.
The typical DC motor of that size probably spins really fast RPM as well, right?
Yeah, exactly. It's a high RPM.
Low load.
Yeah, exactly. Yeah.
Yeah.
Different purposes.
Yeah. I'm not sure, do the Elegoo DC motors come with a gearbox?
Yes, they do.
Okay.
Yeah, they have a little gearbox on the tips that put them to a reasonable amount of speed versus torque.
Yeah. Then the final activity. Do you think you can control the output of a continuous servo using serial input, just like I did with the DC motor? And this time I want you to consider the fact that you shouldn't abruptly change the speed or direction of a motor, because if you think about it, for example, let's say you're skating down a hill and you suddenly want to go back up the hill. And so you can imagine that that's going to be a really hard task because first you have to slow down and stop and then go back up the hill. And so it's the same thing with motors. You don't want to suddenly change the direction because that could cause a spike in the current that the motor draws up. And if the motor cannot handle that spike, it could get damaged. And if the electronics cannot handle that spike, they could get damaged. And so in order to safely change the speed of a motor, you might want to gradually increase it to the desired speed. So we kind of did that before with the sweeping motion. Remember, it's kind of gradually increasing or decreasing the speed. And so if you look at the pseudocode for this program, so first off, you want to set up the servo, the serial, and also set an initial speed variable. And then in the loop function, you want to check if there's anything typed in the serial terminal and store that number in a variable. And if the given speed from the serial value is greater than the previous speed, then you want to gradually increase the speed to the desired speed. But if the speed given from the serial terminal is smaller than the speed that you had previously, then you want to gradually decrease the speed to the desired speed. And if the two values are the same, then you don't want to do anything. And at the end, you want to set the previous speed to the current speed. So basically updating the speed. So think about that. Try to adjust your code to take input from serial. Like, you don't have to be part of this, but if you can, that's even better. Because in the future, that'll just protect your hardware.
Yeah, that is a good point, actually. In FRC robots, if you want to take away a lot of the jerkiness from the robot, you don't allow instantaneous speeds. You do smooth that out with some software.
Yeah. So any questions on that? So I'll give you a few minutes to try it out, and then I'll show you what I did for this.
And maybe in the meantime, you can put up that slide that had the serial input. It'll just probably serve as a good model.
Oh yeah, of course. So this is the code to.
Perfect. And there's a question there, when are we planning on getting our Elegoo robots? The answer is soon. I think we're targeting for about a week to start distributing it to mentors. That's not 100% sure, but if I'm trying to think of all the dates, we've been trying to line things up because we want to give you the robot, the cups, the game mat, and the kit apart, so those extra electronics. So yeah, so all those things have to come together. I haven't been directly involved with ordering, but we're waiting on a couple of things that we think will be coming the week of March 11th, maybe something like that. So definitely not this week. Possibly next week if we really get things kind of as fast as we think we could. But then there's probably a pretty good chance of the week of the 15th. So that's my hope anyways.
Nice.
It's not official, don't quote me, despite the fact this is being recorded.
Yeah, we should, the Elegoo workshops should start by then, right?
Yeah, they were talking about giving us maybe a week or two off on the programming side because there's a lot of mechanical and CAD workshops that need some time to work through. Plus, until we have the Elegoos, it's going to be of less value to do it. So we might as well wait till we have them in our hands.
Yep. Any questions? So feel free to ask them.
Does anybody want more time or should we proceed to the solution? If you need more time, put the no symbol on or something and we'll wait a little longer. Almost done. There you go. Jeff's almost done.
Yeah, that's the last thing.
I think he means he's almost done writing up the code.
Oh.
But yes, this is also the last thing. So
Yeah.
it's a good amount of practical stuff that you can directly apply to your Elegoo when it comes. So that'll be nice. It's probably the closest session we have had to what you're really going to do.
Yeah, and hopefully you can connect this to the next workshop of sensors. So instead of using serial, you can then use the sensor inputs to control the motors.
Yeah, then you really have a robot that can react to its environs.
Mm-hmm. So if you're ready, just click the check icon. Okay.
And for anybody who's doing this on the recording, if you can't figure this out on your own after you've seen the solution, feel free to go to our Discord server, and you can go to the general channels and then go to the workshop discussion channel in there and type up any questions you have. We have a lot of senior students and mentors that are monitoring the Discord server, so you'll get an answer pretty fast.
Yep, and feel free to drop questions right now. And if you want me to put up anything, any code or any slide, also let me know.
So I think we got one check mark that we're done. And if you're not getting this, don't feel bad. It is if you haven't had a background in this before at all, it can be quite a bit challenging. Oh, there's another thumbs up there. Another one. Yeah, I think we're pretty much there. I think you can go ahead and start working on the solution.
Right. Looking at the pseudocode, we said that we want to set up the servo, the serial, and also initialize the speed. So I have three variables. One is for the current speed, or the speed that you want to get to. And the previous speed variable is the speed of the motor at the last iteration of the loop, or getting serial. And so this speed is just the variable for the loop. And you set up the serial, the servo, and then in the loop, it's just basically the same loop we had, the same code we had here. Make an array, read from serial if there's anything, and convert it to int, and store it into current speed. And then if you look back at the pseudocode, if the current speed is greater than the previous speed, then you want to gradually increment the speed and have a small delay in between each command. And if the previous speed is greater than the current speed, then you want to gradually decrease the speed until it reaches the speed that you want. And you also have a small delay. Now at the end, you update the speed. So you set the previous speed to current speed. So next time when you reiterate through this loop, then you'll have basically the new speed that you want to gradually change from. So I think I went a little quickly through that. Any questions? currently it's at 0. You can set it to 60, which will slowly speed it up. And the simulator might not be perfect in showing that it's gradual, but if you actually had a servo, you'd see that it's slowly getting up to speed. Now we can change the direction, and it will slowly change to the other direction. And that way you don't overload your motors with commands.
So hopefully the gist of that makes sense to you. It really is kind of a stepping up towards your target. If you are doing really fast control of something, your code may need to be expanded. Like this is a bit of a simplified example, because while you're doing this ramp up in speed, your code is actually not reading the next speed that you set it to. So if you were to set a new speed in the middle of this changing speeds, your robot would not respond until later. So you got to be a little careful when you're doing like a joystick, for example. If you have your analog sticks and you're reporting a certain speed, you can't have your loop kind of busy ramping up or ramping down, because it'll start being slow in responding. On the flip side, because you've got analog sticks, they're kind of real world, you're not going to switch too fast, because your thumb actually has to move from one position to the other. So that'll put in some natural smoothing to your speed. So just to keep in mind that if you try this in your code at the end, you're like, hey, it doesn't work. It seems to be really slow on responding. That's kind of the idea. So then you have to go to the next step and think about how you can do this smoothing either a little faster or a little less aggressively, maybe bigger steps, and that kind of stuff. So instead of going speed ++, you could speed an increment by 10, something like that. So of course you got to be careful about bounds and whatnot, but this is a good starting point.
Yeah, you could also always change the delay. You could set it to 5 if you want it faster.
Yeah, that's right. You can do a little bit of math and go, all right, if I'm going from as far as one end of the speed spectrum to the other end of the speed spectrum, that's going to take me, say, whatever, 100 steps, and that's 100 steps times a delay of 10 milliseconds. So how long is that actually going to be? Is that too long, or is that long enough? So a little bit of math will save you some practicing too.
Yep. So any final questions?
All right, well, we covered a lot of really good stuff, and as I said before, it is complicated. This is where your code hits real world, and real world is ugly. So don't get discouraged. Keep working at it, and good luck on your challenge.
Yeah.
And thank you, Lila.
You're welcome. All right then.